All right, hi everyone. Thanks for joining us here this evening. My name is Charles E. Brechtel. The E is for Ezekiel, which is where my nickname Zeke comes from. I'm a senior at Ohio Wesleyan University studying physics and mathematics. And my project here on the Juno Ice Field was mathematical modeling of katabatic wind flow. All right, so katabatic wind flow is this characteristic wind that we can observe on glaciers that's pretty uniform, and it's always blowing downslope along the glacier. And so what happens on these glaciers is closer to the surface, the temperature of the air is going to be a lot lower, essentially close to 0 degrees Celsius. And thus, because the temperature is lower, the density of the air will increase. So relative to another point further out along just the downslope axis, the density of the air differentiates a lot, and so this creates a pressure differential, meaning that at this point here, say if this is x1, the pressure is going to be greater than further out at this point here. And so this pressure differential is represented by this sloping graph here. And so because of this pretty much continuous pressure differential, the system wants to reach a state of equilibrium. So it's pushing the denser air down the slope of the surface of the glacier, and we get this continuous downslope wind. So that's what katabatic wind is, and to give you guys an idea of what you might see on a glacier surface, I included this graph. And so looking at height above this glacial surface here, we see that lower down closer to the surface, we have these pretty heavy katabatic winds, which are around 6 or so meters per second, and these are all pretty much blowing down slope. But as we move further up, we eventually reach a point where the wind starts blowing in the opposite direction. It's actually blowing upslope, so around 300 meters or so, we kind of lose all sort of katabatic effects that we've been observing. So to measure katabatic winds on the Taku Glacier, I had this awesome looking profile mast. And so at varying heights along the profile mast, I had anemometers here to measure air velocity, and I had thermometers to measure temperature. And as you can see, we got to set it up on a beautiful day. We set up quite a few cameras and did a pretty great photo shoot. So it was a lot of fun, and it looked really great when I got everything all set up. So after spending the summer on an ice field and having such an incredible experience being outdoors, I figure it's probably about time for me to get back to my natural environment, which is in the basement of my school's science center, sitting behind a computer screen. And that's where I get into some of the other fun stuff, which is the mathematical modeling. So what I'll essentially be doing is trying to represent the behavior of these katabatic winds from a mathematical and physical consideration standpoint. And so we do this by considering a lot of equations that define fluid motion, and skipping all the fun stuff, we get these two simple equations, which are known as the Prandtl model. So as far as meteorological equations and models go, these are pretty simple. And right here we have the temperature profile as a function of height, and the wind speed profile downslope along the glacier as a function of height. So the behavior of these equations is, this graph gives you guys kind of an idea of what we'd expect to see. So for the wind speed, we expect it to be 0 close to the surface of the glacier. And then as we move up above the glacier surface, basically, we expect to observe a wind speed maximum right here at some point, and then expect the wind to taper off again the further we move up. And at the same time, with the temperature, we expect it to be at a minimum right at the glacier surface, because that's where the ice is. And then as we move further up, the temperature will increase. And so what I have is a lot of great data that symbolizes all this. I've got about 1 million data points I figured out with a rough calculation. And I just plotted all of my anemometer data and thermometer data at varying heights on this axis to give you guys an idea of what I'm dealing with in general. And so this section right here is pretty fairly indicative of what we're looking for in the katabatic winds. So I thought I'd zoom in on it and just point out some of the features. We see that the wind speeds are at the maximum at the height 9.1 meters here, and then it kind of decreases as we move down. So that's a little discouraging because we don't see a definite maximum and then decrease, but we'll look at areas like this where it's looking more symptomatic maybe. And then we have the temperature definitely decreasing as a function of height above the glacier. And then we also can observe some interesting, I guess, anomalies, you might say, where we have these temperature spikes corresponding with an air velocity decrease. So essentially, for all my future work, I'm going to be looking at all this data and seeing what sort of anomalies I can observe like that, figuring out which data points are most indicative of a katabatic wind flow, and eventually modeling this katabatic wind flow using the Pranzel model. And then as some possible much further work in the future, we had a weather station set up on the Nunatak above the Taku Glacier, and we're hoping that this will demonstrate some upslope flow of a wind, and we're hoping that we can somehow draw a connection between our Pranzel model and this upslope wind behavior, and kind of coupling the two to further develop a model of what wind essentially behaves like above a glacier. So thank you to my advisor, Dr. Craig Jackson, and everyone on the Juneau Icefield Research.
All right, hi, my name is Kristen Tim, and I'm a graduate student at the University of Alaska Fairbanks in Science Communication, and I participated in the Juneau Icefield Research Program for two main reasons this summer. One was to gain some experience in different areas of science that I wasn't exposed to previously, but the second piece was to actually coordinate some outreach activities during the field campaign, and that's what I'm going to present to you today. So why bother with science communication or outreach activities? There's several really good reasons to incorporate these activities into scientific campaigns. And one of them is to excite future generations of scientists and future generations of JIRPers, inform policymakers and the public, not just about the science activities that are being done, but how the work is actually done up on the ice field, and what life is like on the ice field in addition to the science, because there's a lot of fun things that happen in addition. So also we're working on building collaborations between different disciplines in the science, and also between scientists and non-scientists, to just make more valuable research results and come up with really innovative and new projects. And then finally, several funding agencies actually require scientists to have outreach components to their projects now, and it's a great way to give back to the community and the taxpayers that make this work often possible. And finally, we just want to try to positively reflect the sciences as something that's not just people in lab coats, but people out in the field doing really fun and interesting things. So this is the first year that the Juneau Icefield Research Program has had kind of a coordinated outreach effort from the field. And this is me climbing up a little mountain behind one of our camps. And this was sort of the first mountain I feel like I've ever really climbed in Alaska. And this is kind of a baby step to greater things. And like JIRP, you know, we're taking baby steps towards hopefully what will be a more robust program in the future. But for right now, we had a blog, we incorporated photo and video and social media into the outreach campaign, and then presentations in Atlin and Juneau, and then some media outreach. So a couple interesting things about our blog. We felt like this was a pretty successful outreach effort that we had. 7 continents, 906 cities, 54 countries, thousands of visitors, actually more than 43 posts. I think it's up to 50 some now. And people spend about 3 minutes on the website, which is actually pretty good in the website world. So people are actually reading our blog posts. And where did blog visitors come from? Well, not a big surprise. We had a lot of visitors come from the towns that we as the JIRPers came from. So we had lots of family and friends following, but You'll see that there's also groups of people in Europe and in Asia that were following the blog, so this is pretty exciting. So just in conclusion, I just want to encourage you all, even though the expedition has ended, the blogging hopefully has not ended. And you got a little picture of some of the things that we did out on the ice this summer, but there's a big picture that's been painted online. And so as you go out the door, there's some little slips of paper out there, and it has the link to the website, glacierchange.org, which is where the blog was hosted this summer. So go back and read and learn about everything that we did, and not just the science, but you know, what it's like to live up there and be up on the ice field. And just in conclusion, I want to thank all the JIRP faculty and staff and students, because this was a joint effort. We all, you know, wrote blogs and took photos and shared our own personal stories. Thanks to Jamie, who's here in the back, and Matt. This is actually Matt's blog, and both of them did a lot of work to make this all possible. And then the UAF Resilience and Adaptation Program for actually funding me to participate in this summer. So, thanks.